This is a revision video for Unit 8 of AQA GCSE Chemistry, Chemical Analysis. You may find this useful if you're revising for an end-of-topic test or maybe your final GCSE exams. Chemical analysis comes up in Paper 2 of both GCSE Chemistry and GCSE Combined Science. In this video, we'll look at pure substances, mixtures and how we can separate them, formulations, chromatography and gas tests, which are all for combined scientists. And then just for those taking GCSE Chemistry, we will also cover flame tests and test tube reactions to detect anions and cations. Firstly, in the chemical analysis topic, we need to talk about pure substances and mixtures. And this can be a little bit frustrating because the word pure is already part of your vocabulary and you're already very comfortable using it. But unfortunately, not only do we mean something slightly different in chemistry when we say pure, but actually you're expected to be able to use both definitions within the exam. So in ordinary circumstances, if you were to talk about something as being pure, maybe some pure orange juice, what you would mean is that nothing had been added to it, nothing had been done to change it. We might describe it as being unadulterated. So this very simplified picture that I've drawn here shows you that within some orange juice we have some water molecules, but we also have some sugar molecules. And they haven't been added, they came straight from the orange, but they're both in there mixed up together. In contrast to that, in chemistry when we talk about a pure substance, we mean either a single element or a single compound that's not mixed with any other substance. So within my box, I only have water molecules, and that would be my chemistry definition of pure. Now, since those mixtures exist, we need ways of splitting them apart to get the individual components, and we can do this using physical processes. A physical process doesn't make any new substances like a chemical reaction does. Instead, it uses a method like heating or cooling or filtering to split apart the different parts of the mixture. You need to be familiar with 5 different physical processes that can be used to separate mixtures: filtration, crystallization, simple and fractional distillation, and chromatography. Filtration is used to separate insoluble solids, so that means solids that won't dissolve, from liquids, and this is done by passing the mixture through filter paper. The residue, which is the insoluble solid, will stay on the filter paper, while the liquid and any soluble solids that are dissolved in it will pass through the filter paper. If you're trying to get a pure dry sample of a soluble substance, something like salt or copper sulfate, then filtration is no good because that soluble substance could just pass through the holes in the filter paper. So instead we use a technique called crystallization. In this, we put our salt solution into an evaporating basin and then very gently warm it using either a hot water bath or an electric heater until most of the liquid has evaporated. Then we remove the evaporating basin from the heat and leave the contents to cool and eventually crystallize. Simple and fractional distillation can both be used to separate mixtures of liquids depending on their boiling point. The difference is in the number of different liquids that we're trying to separate. So for simple distillation, we're only going to extract one product, whereas for fractional distillation, we're going to extract several. We're going to look at chromatography in more detail because it's one of the required practicals. But in addition to being a separation technique, it's also an analytical technique. So it doesn't just split up the different components of a mixture, but it helps us to identify what they are. In addition to separating out mixtures into pure elements or compounds, we need to be able to demonstrate that a substance is pure, and one way we can do this is by looking at its melting point or boiling point. Pure substances have a single unchanged melting and boiling point, which can be looked up in a data book. So for instance, we know that pure water boils at exactly 100 degrees C, and therefore if a sample of water doesn't boil at 100 degrees C, then it can't be pure. You know from GCSE physics that when you heat a pure substance, you get a graph with a particular shape. To begin with, as we heat the substance, the temperature increases. And then when that substance reaches its melting point, there's a part of the graph where the temperature doesn't increase, and the same is true when it reaches its boiling point. The reason for this is that rather than energy being used to increase the temperature, it's being used to overcome the forces between particles so that the state change can happen. Now, if we have a substance that isn't pure, then that state change is going to be happening at slightly different times. So we end up with a slightly wonky graph, maybe something that looks a little bit like this. The overall shape is similar, but we no longer have those flat portions, and that is a key indicator that the substance you're looking at is not pure. A formulation is a mixture that is designed as a useful product by carefully controlling the different quantities of the different ingredients that are used to make it. Formulations include fuels, cleaning agents, paints, medicines, alloys, fertilisers and foods, and all of those have very carefully controlled things that are put into them to ensure that the properties are consistent. An alloy is a mixture where the primary component is a metal. Pure metals and alloys have different properties to one another. Alloys are harder. If we look at a pure metal at an atomic level, all the ions are one size because they're all the same element and they form these regular rows. So if you hit a pure metal with a hammer, it's possible for one of those rows to slide over the other rows, and therefore this makes the metal malleable. If you compare that to an alloy, the ions are different sizes because they've come from different elements. So therefore the regular rows are distorted, and if you exert a force on an alloy, those rows can't slide over each other, and this makes alloys harder. Alloys present a really good opportunity for the exam board to examine not just your chemistry knowledge, but also your math skills, and also to ask you some suggest questions. Remember, a suggest question doesn't have a specific right answer that you've learnt, it's asking whether you can figure something out. So we could be asked to read some values from a graph and also suggest reasons why alloys are used. So that could include things like cost, although some questions will say to you don't refer to cost, but also hardness, and also the fact that there are lots of different types of gold of different colours. And then in terms of what would happen to the properties of the gold, well, we know that this is going to make the metal harder. One way that you can identify whether a substance is pure and which different substances it contains if it's not pure is by using a separation technique called chromatography. There are several different types of chromatography, but in GCSE Chemistry you'll mainly have encountered paper chromatography because that's one of the required practical activities. All types of chromatography are used to separate mixtures and analyse what is in them. Chromatography is a comparative method, which means rather like fingerprinting, it can't tell you anything unless you have something to compare your samples to. All types of chromatography use a stationary phase, which remains still. So in paper chromatography, that is your chromatography paper. And then a mobile phase, which moves through the stationary phase, transferring the sample. In paper chromatography, this is a solvent such as water. The substances are separated out based on how well retained they are by the stationary phase. In paper chromatography, this will correspond to how soluble they are in the solvent. A very soluble substance will travel with the solvent for a long distance and therefore be retained for a long time, whereas a less soluble substance will be deposited on the paper after a shorter distance. For the required practical, you had to set up and analyse a paper chromatogram. This is usually comparing a few different felt tip pens to see whether they contain the same mixture of inks. In setting up the experiment, there are some key points to note. You need to draw a start line to ensure that when you analyse the results, you know how far the sample has travelled. This should be drawn in pencil because a pen might run and interfere with your results. Whichever solvent you're using for your mobile phase, this should start below the pencil line. If you add too much solvent, or if you don't have some way of stopping the chromatography paper from falling in, then your samples will just run out into the solvent rather than being drawn up the paper. If you're using a particularly volatile solvent, you need to use a lid to prevent it from evaporating. As we said, chromatography is a comparative method, and the simplest way to compare your sample to other substances is by putting a little of each of these on the same chromatogram. We call these known substances standards. At the end of your chromatography, you could say that you will calculate an RF value for each ink or dye or colour, and we'll look at how to do that in just a second. So you can see here I have the start line drawn in pencil, I have one standard to compare my sample to, I'm using a splint to stop the chromatography paper from falling down into the solvent, and then finally on the right hand side you can see the finished chromatogram. We can analyse our results for chromatography both qualitatively and quantitatively. In terms of the qualitative conclusions we can draw, we will do this by looking at the number of spots and comparing these to spots of the standards, those known chemicals where we already know what they are. It's important to note that a pure element or a pure compound will produce a single spot in all solvents. So you could have two substances within your sample that have the same solubility in water. And when you did your chromatography with water, you just got one spot because they'd landed in exactly the same place. but it's very unlikely that they would have the same solubility in multiple different solvents. So you could then do your experiment again using, say, ethanol as a solvent, and if you still only got one spot, then that would be a very good indication that your sample only contained one substance. So each of my 6 standards here are pure substances because they have only produced a single spot, but my sample contains 3 different substances. It's probably worth pointing out here that we often use paper chromatography for different colours or different inks, so your exam board may phrase this in terms of how many different colours are in the sample, and this can confuse a lot of students because of course your exam paper is printed in black and white. So when they're asking you how many different colours are there, what they're really asking is how many different spots are there. So my sample here has 3 different spots, therefore I would be saying it contains 3 substances or maybe 3 colours. I'm then going to compare those 3 dots for my sample to the standards. So you can see that I have 1 dot for my sample that is at the same height as the dot for the standard A. And that tells me that my sample contains substance A. And then I have another dot at the same height as substance B, so my sample contains substance B. And then there's a 3rd dot, and that doesn't correspond to any of my standards. So I can't identify it because this is a comparative technique. But I do know that there is a 3rd substance, and I can say conclusively that my sample doesn't contain C, D, E or F because I don't have a dot that corresponds to any of those. Now, in a classroom situation, you might have been given a sample of ink to test, and you might have had 3 different pens that it could have come from. So it would be quite realistic for you to run one single chromatogram with your sample of ink and the 3 different pens put in there as standards. And then you could just look at them all and compare have the different samples got to the same height. But when we're thinking about industrial chemical analysis and maybe trying to analyse a sample for hundreds or even thousands of different compounds, it just wouldn't be realistic to put every single one of those standards on the same chromatogram as the sample. It would need to be a huge chromatogram, and also we would be using up huge amounts of those samples to include them every time we try to analyse something. So we need a way to be able to compare our sample to those standards without running them every single time. This is where we start to use RF values or retention factor values. So the idea of an RF value is it's a numerical value that tells you how soluble a particular substance is. And we calculate it using a fraction, where the distance that the substance travelled is divided by the distance that the solvent travelled. So obviously the distance that the solvent has travelled is the maximum distance that the substance could travel, because our coloured ink isn't going to suddenly jump ahead of the solvent that it's being carried by. So if a substance is super soluble and it stays in that solvent for a long time and it doesn't get deposited until the very end of the experiment, then we could feasibly have an RF value of 1, because the distance that the substance travels and the distance that the solvent travels will be the same. At the other end of the spectrum, if we had a substance like standard C here, which was completely insoluble and didn't move off the start line at all, then we would have an RF value of 0. And then most substances are going to fall somewhere between those. So when you calculate RF values, they must be between 0 and 1. And this sort of represents 0% to 100%. You can't have something that's gone further than the solvent has. A substance will have different RF values if you test it with different solvents, but those values will be constant. So for instance, if you have an ink that has an RF value of 0.8 in water, it will always have a value of 0.8 in water. But if you tested it in ethanol, then it might be 0.7, and it would always be 0.7 in ethanol. So in order to do this calculation, I'm going to need to measure the distance travelled by the substance, and I'm going to measure that from the start line to the very centre of that dot. And then I need to measure the distance travelled by the solvent, so we call that line that the solvent has got to the solvent front, and then I would divide the length of that blue arrow by the length of that green arrow, and I would get a number between 0 and 1. These are pretty straightforward calculations, but it's worth having a little practice. Now, you might prefer to use an instrumental method rather than a human method, and this applies to all sorts of situations, not just chromatography. Why would we rather use a digital thermometer and a data logger rather than standing there and measuring a reaction with a thermometer? The 3 key advantages are that instrumental methods are accurate, which means they're more likely to give an answer that is close to the true value. They're rapid, or in other words quick, and they are sensitive. So they are able to detect very small quantities of a substance or very small values in a change like temperature or mass. On the other hand, disadvantages of instrumental methods are that they may be more expensive and they may still require highly trained personnel in order to operate the equipment. Next, there are 4 gas tests that you need to be able to describe. This boiling tube contains hydrogen peroxide, which breaks down naturally over time to make water and oxygen, and this is how I'm going to make the oxygen to do my gas test. Now this happens quite slowly naturally, so I've just added some catalyst called manganese dioxide to speed things up. The gas test for oxygen is to use a glowing splint. So I'm going to take a lit splint that's been set on fire and then blow it out, and this will relight in the presence of oxygen. So here's my lit splint, which I'm then going to blow out. And now if I take this glowing splint and I put it near to this gas, you can see that it's going to relight. The second test is for hydrogen, which burns rapidly if you ignite it, making a popping sound. Definitely hydrogen. This is often referred to as the squeaky pop test, but unfortunately that name won't get you marks in an exam. So remember to talk about setting it on fire and how it burns rapidly with a pop. You can test for chlorine gas using damp litmus paper. It doesn't matter whether it's red litmus paper or blue litmus paper, but it must be wet or the test won't work. To test for carbon dioxide, the gas is bubbled through lime water, which then turns cloudy as a white precipitate is formed. This solution of aqueous calcium hydroxide, commonly known as lime water, reacts with small amounts of carbon dioxide to make a white calcium carbonate precipitate, a solid that makes the solution turn cloudy or milky. Many cations, in other words positive ions that are formed when metallic elements lose electrons, produce characteristic colours when they're burned. This means that all compounds that contain a particular cation will burn with the same colour. If I burn a compound that contains lithium ions, then I see a flame that is crimson, this dark pinky red. If on the other hand the compound contains sodium ions, it will burn with a yellow flame. And if it contains copper ions, then I see a green flame. There are 5 cations for which you need to know the characteristic flame colours. As we've already seen in this video, lithium compounds burn with a crimson flame, sodium compounds burn with a yellow flame, and copper compounds burn with a sort of turquoisey bluey green flame. You also need to know that potassium compounds burn with a pale lilac flame, and calcium compounds burn with an orange-red or brick-red flame. The first step in carrying out a flame test is to clean a nichrome wire. We use this nickel and chromium alloy because it has a very high melting point and because it doesn't produce a flame colour of its own. We use a Bunsen burner to remove any dust, and then place the wire into a small beaker of hydrochloric acid. The acid will react with any leftover metals from a previous test, removing them, so we can be confident that when we put the new compound on the wire, the flame colour that we're seeing is just from that compound, it's not from anything left over from a previous test. The hydrochloric acid will also moisten the wire, and that's going to allow us to easily pick up a solid salt, although you can also do this test for solutions. You just tend not to get as bright a colour. So here I've got a small amount of copper compound, you can see it there in my spotting tile. So I put the wet wire into that copper compound, that copper sulfate, and then put this into the edge of the clear part of a Bunsen burner roaring flame, and you can see that greeny blue flame there. Before I can do another test, I need to return it to the hydrochloric acid to make sure that I have removed all of that leftover copper compound. Now that the wire is clean, I can repeat the same test, only this time using a lithium compound, and again I see that crimson, dark pinky red flame. One of the biggest problems with flame tests is that if you have more than one cation present, then the colours will obscure each other. Say for instance I have a mixture of lithium and potassium, the pale purple lilac colour of the potassium flame would get completely blocked out by that really vibrant crimson colour, and so I'd be able to identify that lithium was present but not potassium. This is one of the problems with this method. To get around this, we can instead employ an instrumental technique called flame emission spectroscopy. As we know, instrumental techniques have three big advantages. They're accurate, which means the answer they give is likely to be very close to the true value. They're rapid, or very quick, and they're sensitive, so they can detect very small amounts of a substance. In flame emission spectroscopy, the sample is put into a flame, and then the light that comes out is passed through a spectroscope, and this produces an output called a line spectrum. The position of the lines on that line spectrum correspond to the different wavelengths of light. So blue light with a sort of wavelength of about 700 nanometers would be at completely the opposite end of the spectrum to red light with a wavelength of about 400 nanometers. We can compare the positions of these lines to say whether or not a particular element was present in a sample or not. The thickness of the lines corresponds to how bright the light was, and that corresponds to how much of the substance was present. So if we're thinking about a solution, then this would be the concentration of the ion in that solution. Some cations can also be identified by testing them with sodium hydroxide. While sodium hydroxide is a colourless, soluble substance, the other hydroxides that are produced are not soluble, and therefore they form precipitates with characteristic colours. So first up, I've got copper. And if I add the sodium hydroxide, you can see it was already blue, but now at the top you can see there's a sort of a blue solid, a blue precipitate being formed, and that is copper hydroxide. And then likewise, this next one is iron 2+ ions, because remember, iron being a transition metal has multiple stable ions. So these are the iron 2+ ions. And they produce this characteristic sort of dark green colour. And then in contrast to that, iron 3+ ions produce a much more orangier colour. Now, my last three are a little bit harder to tell the difference between because they all form white precipitates. So these are calcium and magnesium and aluminium salts, and you can see they don't look identical to each other, but they are all forming a white precipitate. So that's not hugely useful. It means I can tell that it's one of the three, but I can't tell which one it is. However, if I add an excess of sodium hydroxide, then aluminium ions will redissolve. So if we have a look at that, still very much precipitate. Still not really seeing any change. But with this last one, it's not very easy to see on the video, but around the sides we can see it starting to redissolve. If I lift the camera up slightly so you can see the top of the tube. The top of the tube is starting to sort of clear out, and that is very much starting to redissolve. If I compare it to the other two, you can see they're still opaque, they still have precipitates, but my aluminium is separating out. Now, if I wanted to tell the difference between the calcium and the magnesium, there is a way I can do that, and I could use a flame test. You need to be able to write symbol equations for 5 out of those 6 reactions. You don't need to write them for aluminium because this is actually slightly more complicated chemistry that we don't cover until year 13. For each of these ionic equations, you're going to start off with your metal cation, which has either a 2+ or 3+ charge, and then the aqueous hydroxide ion, which has a single negative charge. In the final compounds, the positive ions need to be balanced out by the negative ions so that the overall compound has no charge. And so the number, the magnitude of the cation, is going to tell you how many hydroxide ions you need. So for the first 4 ions with their 2+ charges, you need 2 hydroxide ions, and for the final one, you need 3. Now, because we're talking about multiples of that whole hydroxide ion, when we come to write the symbol for the final compound, we're going to use brackets. So here you can see I started off with 2 hydroxide ions, now they're in that compound, but I want to make sure that I'm including 2 hydroxide ions, not just 2 oxygen, not just 2 hydrogen, so I've put that in brackets. And so it's going to look very similar for the next 3, and then for our final one we're obviously going to have 3 hydroxide ions. The reason that the symbol equations are harder than the ionic equations is that you now need to be mindful of the extra spectator ions, those anions that are bonded to the cations we're interested in at the start. So if we start off by just looking at the cations in turn and figuring out what the formula that a hydroxide would be, just like we did with the ionic equations, we can do this quite straightforwardly. So for the first 4 with their 2+ charges, we're going to have 2 hydroxide ions, and then for our iron 3+, we're obviously going to need a 3rd hydroxide ion. So now you need to look at the anion in the compound on the left and figure out how many singly charged sodium ions are going to balance that out. So in my first example, I've got chloride ions, and chloride ions have a single minus charge, so when they make a compound with sodium, it's just NaCl. But we don't have 1 chloride ion in our first equation, we have 2, so it's going to need to be 2 NaCl. And therefore, to get the 2 sodium that I need for that, and also the 2 hydroxide that I need for the copper hydroxide, I'm going to need 2 lots of sodium hydroxide. The second example uses iron 2 nitrate, and I already know this is going to make iron 2 hydroxide, and each one of those nitrate ions has a single negative charge. If I didn't know that already, I could figure it out by the fact that it takes 2 of them to balance out the iron 2+. So each one of those nitrate ions, just like the chloride ions in the previous example, is going to go in a 1-to-1 ratio with sodium to make NaNO3. So then, just like in the previous example, I'm actually going to need 2 sodium nitrate to use up both of the nitrate ions that I have. And therefore, I'm going to need 2 sodium hydroxide. The third example is slightly trickier because it involves a sulfate ion, and a sulfate ion has a 2- charge. So therefore, my second product is going to be sodium sulfate with a little 2 after the sodium. And therefore, we're going to need 2 sodium hydroxide. Then for my fourth example, magnesium bromide, a bromide ion behaves just like a chloride ion. So again, we get 2 sodium bromide and 2 sodium hydroxide. And then my last one is a really nasty example. So again, we've got our sulfate ions. So our second product is going to be sodium sulfate. But because we've got those 3 sulfate ions in my original compound on the left-hand side, I'm going to need 3 sodium sulfate. And therefore, I'm going to need a total of 6 sodium hydroxide. Next, we need to test for the presence of anions, our negatively charged ions, starting with a sulfate ion. So to test for a sulfate ion, we're firstly going to add hydrochloric acid. This technically isn't part of the test, but what it's going to do is remove other ions that could give us a false positive. Having done this, we're then going to add barium chloride solution, and if we get a positive test, if there are sulfate ions present, then we're going to see a white precipitate forming, which is called barium sulfate. So to start with, I'm going to add a little bit of hydrochloric acid to each tube. And now I'm going to add some barium chloride. And the barium chloride, if there are sulfate ions present, then the barium ions will join up with those sulfate ions to make barium sulfate, which is a white insoluble precipitate. So I'm going to see the solution produce this white precipitate and go slightly cloudy. So if I add some to this tube, not a lot happening, no sulfate ions there. But if I add some to this tube, then I can see that white precipitate forming. We can represent this process with a symbol equation. So here, barium chloride reacts with copper sulfate. We know that barium is in group 2 and chlorine is in group 7, so therefore they form a compound in a 2:1 ratio. The barium chloride reacts with the copper sulfate to form the barium sulfate precipitate. And you can see it's a precipitate because it has an S state symbol standing for solid, and that precipitate is white. Now, of course, it doesn't have to be copper sulfate, it could be any metal sulfate. So we can also use an ionic equation instead, which doesn't contain the spectator ions. So here we have Ba2+ because it's in group 2, and the sulfate ion joining together to make that insoluble barium sulfate. So for this next test, I'm testing for halide ions, and remember that halides are ions that are produced from elements that are in group 7. So here we're looking at chloride ions and bromide ions and iodide ions. We can't use this test for fluoride ions because it's a test that makes a precipitate that's a silver halide, and silver fluoride is actually soluble, so it doesn't make a precipitate. So again, this is a two-part test. We're going to start out and we add some nitric acid, and the nitric acid is in there to remove other negative ions that could give us a false positive. So we put a little bit of nitric acid into each tube, so any carbonates that are in there will react and disappear. And then to those we're going to add some silver nitrate. So for instance, if we have a solution that contains sodium chloride, then the silver ions will react with chloride ions and produce silver chloride, and we're going to see a precipitate. So a little bit of silver nitrate to each tube. And here they are in order. So the first tube contains sodium chloride, or did contain sodium chloride, and it now has, this is a white silver chloride precipitate. And then my second tube with the cream precipitate, that one is containing bromide ions. So this is a silver bromide precipitate. And finally, I've got my iodide ions. So you can see as we go white and then cream and then sort of a pale yellow. So those are the results for my halide test. So to recap, you would add nitric acid in order to eliminate any false positives before adding silver nitrate solution. If you saw a white precipitate, that would be silver chloride. If you saw a cream precipitate, that would be silver bromide, so it would tell you that your original solution contained bromide ions. If you saw a pale yellow precipitate, that would indicate the presence of iodide ions, and fluoride ions would not give you an observable change because silver fluoride is soluble. Again, we can represent these reactions with balanced symbol equations or ionic equations depending on whether or not we want to include the spectator ions. Here I've used sodium chloride as a source of chloride ions, and we basically see a double displacement. So the silver and sodium swap places to make that silver chloride precipitate. And again, you can see the state symbol S because it's a solid, and that precipitate is white. And then there's also some sodium nitrate which remains in solution. We can also write ionic equations that just contain the ions involved in making the precipitate. So if we were still thinking about the chloride ions, it would be this. But if we had bromide ions, then we would make that cream precipitate, or iodide ions, we would make that yellow precipitate. And we can still write an ionic equation for the production of silver fluoride, but as we've said, it's colourless and it's soluble, so we wouldn't actually see an observable change. In the final test, we're checking for carbonate ions by breaking them apart to make carbon dioxide and testing for that with lime water. So here's my calcium carbonate, and I'm going to react that with some hydrochloric acid. And then you can see that I also have a tube here of lime water, so the gas from the reaction is going to be collected and bubbled through that. And you can remember that lime water is another name for aqueous calcium hydroxide. So you can see that at the moment it's colourless and transparent, but in the presence of carbon dioxide it will eventually make a white precipitate. So we make sure that our delivery tube is definitely under the level of the lime water. And then as we pour in the acid, the carbonate is broken down, the carbon dioxide gas is produced, and the white precipitate is formed. Again, I can represent this process using symbol equations, and this time it's going to be in two parts. So in the first equation, I'm taking whatever I'm testing, which in this instance was calcium carbonate. I'm reacting it with an acid and I'm going to make a salt and water and carbon dioxide. And then in the second reaction, I take that carbon dioxide and react it with the aqueous calcium hydroxide, which is the lime water, to make calcium carbonate and water. Now I just want to point out that this first product of the second reaction is always calcium carbonate. Now, coincidentally, that is the carbonate that I started with in my reaction, but it wouldn't have to be. I could be testing zinc carbonate or copper carbonate. But in this second equation, I will always be making calcium carbonate because I'm using calcium hydroxide, which is lime water. Thank you very much for watching, and I hope you're now feeling really prepared for Unit 8 of GCSE Chemistry. If you did find this video useful, then don't forget to like and subscribe for more GCSE Chemistry revision videos coming soon.